Imagine drifting silently through deep interstellar space toward a massive, invisible presence. A black hole announces itself not by light, but by its influence on everything nearby. Stars in the surrounding region move on tight, fast orbits. Gas spirals inward, heating until it glows in Za-Euro's rays. Yet the black hole itself, if isolated and not actively feeding, would offer almost no visual cue. What matters most is not a visible surface, but a boundary in spacetime called the event horizon. This is the region beyond which light, moving at roughly 300,000 kilometers per second, can no longer escape to the wider universe. For a typical Stellar-Euro's mass black hole, perhaps 10 times the mass of the Sun, this horizon sits at a radius of only a few tens of kilometers. For a supermassive black hole in a galactic core, the horizon can span tens of billions of kilometers. As you approach this edge, gravity shapes not only your path, but also your experience of time, light, and causality itself. To understand what happens near a black hole-Euro's edge, it helps to shift from thinking of gravity as a pulling force to seeing it as curved spacetime. General relativity describes mass and energy as telling spacetime how to curve, and spacetime curvature telling matter how to move. Near a massive object, straightest possible paths, called geodesics, bend inward. Far from the black hole, orbits look familiar, like planets circling the Sun. As you draw nearer, the curvature grows stronger, and stable orbits exist only down to a certain critical distance. Around a non-Euro spinning black hole, this inner safe zone for circular orbits ends at roughly 3 times the radius of the event horizon. Closer than that, circular orbits are no longer stable. Matter in an accretion disk crosses this region and begins its final inward plunge. Light itself has a special circular orbit at about 1.5 times the horizon radius. This photon sphere is not a quiet track, but a precarious path where even a small disturbance sends light either back out or in toward the horizon. The term event horizon refers not to a physical surface, but to a boundary in the geometry of spacetime. It divides events that can, in principle, send signals to distant observers from those that never can. If something crosses the horizon and tries to send a light pulse outward, that light still travels locally at the speed of light. However, spacetime itself is so strongly curved that all possible future paths lead deeper inward rather than back out to the universe. This is why, from the viewpoint of distant observers, nothing that passes the horizon can be seen again. The horizon radius depends only on the black hole-Euro's mass, spin, and electric charge. For a simple, non-Euro spinning, uncharged black hole, the Schwarzschild radius is roughly 3 kilometers per solar mass. Multiply by 1 million solar masses, and the horizon radius grows to about 3 million kilometers. This simple scaling shows that larger black holes have proportionally larger horizons, a fact that strongly affects what you would personally experience near the edge. As you fall toward a black hole-Euro's edge, relativity shapes how time passes. For a distant observer, your signals, such as radio pulses or flashes of light, appear to slow. The light you send climbs out of a deeper gravitational well, losing energy and shifting to redder wavelengths. Your clock, viewed from afar, appears to tick more and more slowly. Mathematically, this effect grows without bound as you approach the event horizon. To the distant observer, you never quite cross. Instead, you seem to freeze just outside, signals fading and redshifting until they become undetectable. Yet from your own perspective, carrying your own clock, nothing special seems to happen exactly at the horizon in classical general relativity. You cross it in a finite amount of your proper time, with no sudden jolt. Locally, the laws of physics look the same as they would in empty space, provided the black hole is large enough that tidal forces remain modest at the horizon. The apparent paradox comes from different observers slicing spacetime in incompatible ways. Closer to the black hole, differences in gravity across your body become important. These are called tidal forces. They arise because spacetime curvature is slightly stronger nearer the black hole than slightly farther away. For a small Stellar-Euro's mass black hole, these tidal gradients near the horizon can be intense. If you fall feet first, your feet are pulled inward more strongly than your head. At the same time, your sides are squeezed together. This combination stretches you into a thinner and thinner shape, a process often called spaghettification. Rough estimates suggest that for a black hole with around 10 solar masses, tidal forces near the horizon are strong enough to rip apart an astronaut long before reaching the central region. However, for a supermassive black hole with millions or billions of solar masses, the same curvature is spread over a much larger scale. Tidal forces right at the event horizon can be relatively mild. In that case, you could cross the horizon without immediate destruction, experiencing a stronger gravity field, but not yet being torn apart. If you were falling freely and carried no instruments that referenced distant stars, crossing the event horizon of a sufficiently large black hole might feel uneventful at first. Your local environment would still obey the same physical laws. Light from other infalling material could still reach you, and you could still move and perform experiments inside your spacecraft. The key difference lies not in what you feel at the precise crossing, but in what your future allows. Once inside the horizon, general relativity indicates that all possible future paths point inexorably towards smaller radii. You no longer have a trajectory that leads back to regions from which signals can reach the outside universe. The horizon acts more as a 1 Euro's way time boundary than as a physical wall. If you fire your rockets inward, sideways, or outward, your efforts may change how soon you encounter the central region, but there is no thrust profile that can carry you back across the horizon. The geometry of spacetime has removed that option from your set of futures. Deeper inside, classical general relativity predicts that spacetime curvature continues to grow, eventually reaching a point called a singularity. In the simplest models, this is a region where densities and tidal forces become infinite, and the known equations of physics break down. For a non-Euro spinning black hole, the singularity is often represented as a point at the center, though in spacetime diagrams, it behaves more like a future boundary than a place in space. For a spinning, or Kea, black hole, the mathematical solution contains a Ringa-Euros-shaped singularity and more complex interior structure. However, many physicists view these singularities not as literal physical objects, but as indicators that the classical theory is being pushed beyond its regime of validity. It is widely expected that a full theory of quantum gravity will modify or remove the singularity, replacing it with some region of extreme but finite curvature. At present, this region remains hypothetical and unobserved, hidden behind the event horizon and beyond the reach of direct experiment. Near the edge of a black hole, the smooth picture of spacetime from general relativity meets the fluctuating world of quantum fields. Even in what is classically called vacuum, quantum field theory describes every Euro's present fluctuations, with particular Euros, antiparticle pairs constantly forming and annihilating. Stephen Hawking analyzed how such quantum fields behave in curved spacetime around a black hole and found a surprising result. From the perspective of an observer far away, the black hole should emit a faint, thermal spectrum of particles, now called Hawking radiation. This emission makes the black hole slowly lose mass over extremely long timescales. For stellar Euros mass and supermassive black holes, the temperature of this radiation is so low that it is effectively undetectable with current instruments, swamped by other astrophysical processes. For a hypothetical tiny black hole, the temperature would be much higher, and the evaporation much faster. The Hawking calculation does not require anything special happening to an infalling observer at the horizon, yet it implies that the horizon has thermodynamic properties like temperature and entropy. The existence of Hawking radiation leads to a puzzle about information. In everyday quantum processes, information about a system Eurostrade's initial state is believed to be preserved, even if it becomes hard to reconstruct. Hawking Eurostrade's original calculation suggested that black hole evaporation is purely thermal, carrying away no detailed information about what fell in. If a black hole eventually evaporates completely, This seems to erase information, in tension with standard quantum mechanics. This issue, often called the black hole information paradox, has prompted decades of research. Many physicists now suspect that information is preserved in some subtle way, though there is no consensus on the precise mechanism. Proposals involve quantum correlations in the radiation, modifications to the nearer Euro's horizon structure, or deeper changes to how spacetime and gravity emerge from underlying quantum degrees of freedom. From the perspective of someone falling in, classical relativity says the horizon feels smooth. Quantum considerations, however, raise questions about whether that smoothness can coexist with unitary evolution of information for outside observers. Attempts to resolve the information paradox have generated several bold ideas about what really happens at a black hole Euro's edge. One proposal, known as the firewall hypothesis, suggests that quantum effects could create a zone of extremely higher Euro's energy particles right at the event horizon. In this picture, an infalling observer would not glide smoothly through, but would encounter destructive radiation at the boundary. This would violate the classical expectation of a calm horizon, but could protect the preservation of information. Another line of work, inspired by string theory, suggests that what appears as a black hole might be better described by a complicated, horizontal Euro-sized object sometimes called a fuzzball. Instead of an empty region with a sharp horizon, the entire interior could be filled with tangled quantum strings and brains. These ideas remain speculative and debated. Current observations of black hole shadows and gravitational waves probe spacetime slightly outside the horizon, but do not yet distinguish clearly between a perfectly smooth horizon and more exotic nearer Euro's horizon structures. Although no signal can emerge from inside the event horizon, the region just outside it can be observed with growing precision. The Event Horizon Telescope has imaged the surroundings of supermassive black holes in our own galaxy and in the galaxy M87, producing ringer Euros-like structures consistent with light orbiting near the photon sphere. These observations give indirect evidence for a compact, dark object with a radius close to that predicted for a black hole of the observed mass. Gravitational Euro's wave detectors such as LIGO and Virgo have recorded mergers of black holes, capturing the final inspiral and ringed-on phases as two horizons fuse into one. The frequencies and damping times of these waves match the predictions of general relativity for black holes with event horizons and no solid surface. Still, alternative exotic objects can sometimes mimic these signatures within current measurement uncertainties. Future instruments, higher resolutions, and longer observing runs may reveal subtle deviations that hint at new physics near the edge. The boundary region around a black hole sits at the intersection of several fundamental theories. General relativity governs the larger Euro-scale curvature of spacetime. Quantum field theory describes the behavior of matter and radiation. Thermodynamics and information theory constrain how entropy and information flow. The edge of a black hole, with its event horizon and strong but finite curvature, acts as a natural laboratory where these frameworks must all work together. Thought experiments about infalling observers, evaporating horizons, and encoded information test the consistency of our theories in extreme conditions. While current observations largely support the classical picture of black holes with smooth horizons, they also leave room for small quantum corrections that may become important over very long times or very small scales. As theory and observation advance, the edge of a black hole continues to serve as a guidepost, indicating where our understanding is strong and where a deeper, unified description of spacetime and quantum reality is still required. Around many black holes, the closest thing to a visible edge is not the event horizon itself, but the bright, rotating accretion disk that forms outside it. Gas drawn from a companion star or from interstellar clouds spirals inward under gravity. As it falls, it converts gravitational potential energy into heat and light. In the inner regions, temperatures can rise to hundreds of millions of degrees, especially around stellar mass black holes in X-ray binaries. The innermost part of this disk does not extend all the way to the event horizon. Instead, it typically terminates near what is called the innermost stable circular orbit, or ISCO. For a non-spinning black hole, the ISCO lies at roughly 3 times the radius of the event horizon. For rapidly spinning black holes, the ISCO can move significantly closer in. The way this inner edge glows, broadens spectral lines, and flickers in time gives indirect but powerful clues about the geometry of spacetime near the horizon and about the spin and mass of the black hole itself. When a black hole rotates, its edge environment changes in subtle but important ways. The spinning mass drags spacetime around with it, a predicted general relativistic effect called frame dragging. Near a rotating black hole, this dragging is so strong that there exists a region outside the event horizon called the ergosphere. Within the ergosphere, no object can remain at rest relative to distant stars. Everything is compelled to co-rotate with the black hole. This rotation alters the location of the innermost stable circular orbit. In the most extreme cases of prograde orbits, where matter orbits in the same direction as the black Hollier-Eurostrade S-spin, the ISCO can shrink to only slightly larger than the event horizon radius. This closer inner edge allows matter to release more gravitational energy before crossing the horizon, potentially increasing the efficiency of energy extraction to levels approaching a few tens of % of the rest mass energy, a value significantly higher than in nuclear fusion processes in stars. Many actively accreting black holes exhibit narrow, collimated jets that extend far beyond the host galaxy, sometimes for hundreds of thousands of light years. These jets do not emerge from inside the event horizon, but their origin is tightly linked to the physics of the edge region. Magnetic fields threading the hot plasma near the inner accretion disk and ergosphere can twist and channel energy outward. One widely studied mechanism, often called the Blandford-Euros-Zednagic process, describes how rotational energy of a spinning black hole can be extracted along these magnetic field lines. Close to the edge, charged particles spiral along the fields and are accelerated to relativistic speeds, forming jets that shine in radio, optical, X-ray, and even gamma-ray bands. The detailed conversion of disk turbulence, magnetic reconnection, and black hole spin into focused outflows remains an area of active research. However, observations of jet power and orientation strongly suggest that the immediate vicinity of the horizon participates in launching and collimating these immense cosmic structures. Although the horizon itself is dark, light passing near it can orbit multiple times before escaping, producing distinctive signatures known as the black hole shadow and photon ring. In a simple picture, the shadow is the dark central region seen against a glowing background, roughly corresponding to light rays that fall inward and do not return to a distant observer. Around this region lies a narrow, bright ring composed of photons that skim extremely close to the critical orbits near the edge, sometimes circling the black hole several times before reaching telescopes. The Event Horizon Telescope has resolved such a shadow around the supermassive black hole in the galaxy M87 and around the compact object at the Milky TM center, Sagittarius A. The apparent size and shape of this shadow depend on the black Hollier-Eurostrade S mass, spin, and the inclination of the viewing angle. Comparing theoretical models of photon trajectories with observed images tests general relativity in the strong field regime near the horizon. Light near the edge of a black hole does much more than simply bend. It also carries information about the magnetic fields and plasma conditions through its polarization. As photons climb out of the deep gravitational well, their paths curve, and the polarization vectors rotate in ways that depend on both spacetime geometry and local magnetic structure. Recent polarized images from the Event Horizon Telescope for M87 and Sagittarius A have revealed polarization patterns that swirl around the shadow, suggesting organized magnetic fields in the inner accretion flow. These observations hint that the plasma near the horizon is threaded by strong, possibly dynamically important magnetic fields that can both support and constrain accretion and jet launching. By comparing measured polarization maps with numerical simulations of magnetized accretion flows, researchers infer properties such as magnetic field strength, orientation, and plasma density. In this way, the edge of a black hole becomes not only a test of gravity, but also a probe of high-energy plasma physics under extreme curvature. The edge environment of a black hole is not static. It flickers, flares, and sometimes reverberates in time. In X-ray binaries and active galactic nuclei, sudden increases in accretion rate or magnetic reconnection events near the inner disk can produce bright X-ray flares. These flashes illuminate surrounding gas and dust, which then reprocess the light and send it back toward us with time delays set by light travel distances. This reverberation mapping allows astronomers to estimate the scale of the inner accretion region and to infer how close emission arises to the horizon. In some cases, quasi-periodic oscillations, with frequencies ranging from a few hertz to hundreds of hertz for stellar mass black holes, appear in the X-ray light curves. One interpretation associates these oscillations with orbital or precessional motions near the innermost stable circular orbits. By connecting characteristic timescales to predicted orbital periods in curved spacetime, observations of variability become another indirect means to probe the geometry near the black Hollier-Eurostrade S edge. When compact objects such as neutron stars or smaller black holes spiral into a more massive black hole, the final stages of their inward journey probe the edge region in a dramatic way. As the inspiral proceeds and the orbit shrinks, gravitational wave frequency and amplitude increase until the smaller body crosses the innermost stable orbit and plunges toward the horizon. The precise waveform of this final phase encodes details of the spacetime geometry, including the mass and spin of the central black hole. For stellar mass mergers observed by LIGO and Virgo, the ring-down phase after merger reflects oscillations of the newly formed horizon settling into a stable state. For future space-based observatories such as LISA, extreme mass ratio inspirals, where a stellar mass compact object orbits a supermassive black hole many times before plunging, should offer a high-precision map of spacetime just outside the horizon. Any persistent deviation from the predictions of general relativity in these waveforms could indicate new physics operating at or near the edge. Classical general relativity predicts that an isolated black hole in equilibrium is fully characterized by only a few parameters, such as mass, electric charge, and angular momentum. This statement is often summarized as the no-hair property. Near the edge, this simplicity implies that the external spacetime should follow a very specific mathematical form, the Kea solution for rotating, uncharged black holes. Observations of motion and radiation near the horizon therefore become tests of this solution. By tracking the orbits of stars very close to Sagittarius A, astronomers examine whether their precession rates and orbital periods match expectations for a Kea black hole of roughly 4 million solar masses. Gravitational wave ring-down signals offer another avenue. The frequencies and damping times of the emitted modes should match those of a Kea horizon. Any systematic discrepancy beyond measurement uncertainties and astrophysical complications could hint at additional structure at the edge, such as fields, topological features, or more exotic compact objects. The matter that accumulates near a black Hollier-Eurostrade S edge is often dilute, hot, and magnetized, forming a collisionless plasma where individual particles can travel long distances between collisions. In this regime, classical fluid approximations become incomplete, and kinetic plasma processes start to dominate. Near the inner accretion flow, particles can gain energy through magnetic reconnection, turbulence, and stochastic acceleration, possibly producing non-thermal tails in the energy distribution. These high-energy particles can emit synchrotron radiation as they spiral in magnetic fields, and inverse Compton scatter lower-energy photons to higher energies. General relativistic magnetohydrodynamic simulations attempt to capture the large-scale behavior of this plasma in curved spacetime, but small-scale processes, such as how exactly electrons and ions share energy, require additional microphysical modeling and sometimes laboratory analogs. The resulting temperature ratio between electrons and ions near the edge strongly influences the observed spectrum. Understanding this plasma microphysics is essential for interpreting horizon-scale images and for connecting theoretical models with multi-wavelength observations of accreting black holes. In quantum theory, the edge of a black hole raises deep questions about how entanglement and geometry are related. Hawkinger-Eurostrade-S original calculation suggests that particle pairs are created near the horizon, with one partner escaping as radiation and the other falling inward. This process appears to steadily increase the entanglement between the radiation outside and the interior. If the black hole eventually evaporates completely, the fate of this entanglement becomes a central issue for information conservation. Some modern approaches suggest that spacetime connectivity itself, perhaps in forms reminiscent of wormholes, could be related to patterns of entanglement in the underlying quantum state. In these ideas, the horizon might not be a simple geometric surface, but an emergent structure shaped by quantum correlations. While no consensus exists, and explicit, testable models remain in development, the edge of a black hole serves as a guiding case for broader attempts to unify quantum mechanics and gravity, highlighting how microscopic information could be encoded in macroscopic geometry. The edges of black holes that may have formed in the early universe, often termed primordial black holes, present another frontier. If such objects exist across a wide range of masses, from asteroid scale to stellar or larger, their horizons would have been present almost since the Eurostrade-S first fractions of a second. The smallest of these, if light enough, might have already evaporated through Hawking radiation, leaving potential imprints in the cosmic gamma-ray background or in constraints from Big Bang nucleosynthesis. Heavier primordial black holes would persist today, their edges interacting with surrounding dark matter and baryonic gas. Ongoing and planned surveys look for microlensing events, background distortions, and dynamical effects that could betray their presence. While current data place strong limits on many mass ranges, a few windows remain under active investigation. If even a fraction of dark matter were composed of primordial black holes, then their event horizons would constitute a widespread cosmic population of edges, quietly shaping structure formation over billions of years. The coming decades promise more refined views of black hole edges across the mass spectrum. Improvements in very long baseline interferometry will sharpen images of supermassive black hole shadows, resolving finer details in the photon ring and polarization structure. New X-ray observatories with higher spectral and timing resolution aim to trace reverberation lags, quasi-periodic oscillations, and relativistic line profiles down to scales of a few gravitational radii. Planned gravitational wave detectors on the ground and in space should record many more mergers and extreme mass ratio inspirals, mapping the near-horizon region with waveform catalogs. At the same time, advances in numerical relativity and plasma simulations will generate more realistic models of accretion flows and jet launching, including kinetic scale physics. Together, these efforts will refine or challenge the standard picture of the event horizon as a smooth, classical surface. Whatever refinements emerge, the edge of a black hole will remain a central arena where ideas about gravity, quantum theory, and high-energy astrophysics continually converge and evolve. The idea of an edge of a black hole changes subtly when the wider universe around it is taken into account. The simplest textbook description assumes an isolated black hole in an otherwise empty, unchanging cosmos. In reality, the universe is expanding, and on the largest scales, its geometry is influenced by dark energy. In a spacetime with a positive cosmological constant, such as our observed universe, there can be not only a black hole event horizon, but also a cosmological horizon. This outer horizon marks a region beyond which light, even moving forever, cannot reach an observer because space expands too quickly. The region between these two horizons becomes a finite causal patch. The edge of the black hole is then only one boundary among several that define what can influence what. Careful calculations must distinguish between the black Hollier-Eurostrade-S own mass curvature and the gentler curvature due to the cosmic expansion. In such settings, the interplay between the inner and outer horizons changes evaporation timescales, accretion flows, and the detailed path that light takes as it skirts the black Hollier-Eurostrade-S edge. Adding electric charge to a black hole alters the structure of its edges in ways that are mathematically sharp, though probably rare in nature. The simplest charged solution in general relativity is called the Reissner-Euros Nordster A tilde paragraph M black hole. In this geometry, there are typically two spherical horizons rather than one. The outer horizon plays a role similar to the familiar event horizon. The inner horizon, sometimes called a Cauchy horizon, marks a deeper boundary beyond which the classical predictability of spacetime breaks down. Small perturbations falling inward tend to pile up near this inner edge, leading to intense blue shifting of radiation. Analytic work and numerical simulations suggest that the inner horizon becomes unstable, possibly turning into a region of strong curvature rather than a smooth surface. Astrophysical black holes are expected to carry only a tiny net charge because surrounding plasma quickly neutralizes any imbalance. Still, the charged solutions offer a controlled laboratory in equations, illustrating how multiple horizons and edges can coexist and how delicate the notion of predictability is near them. When rotation and charge are both present, the theoretical Kerr-Euros Newman black hole displays an intricate hierarchy of edges. There is an outer event horizon and an inner Cauchy horizon, as in the purely charged case, but there is also an extended region outside the outer horizon where no observer can remain at rest relative to distant stars. This is the Ergorgen, bounded on the outside by the static limit surface. Within this zone, frame dragging is so strong that all timelike paths are forced to co-rotate with the whole. The boundary of the Ergorgen is not an event horizon. Particles and light can still escape if their trajectories allow. Yet this edge has physical significance. It defines where energy extraction processes, such as the idealized Penrose process, can in principle occur. Mathematics even permits exotic trajectories that circle through the inner horizon and re-emerge, but detailed analyses indicate that instabilities and quantum effects probably prevent such smooth passages in reality. These richly layered edge structures push theoretical tools to their limits and help map the boundaries of classical relativity. The edge of a black hole is not just a geometric surface. It also behaves like a thermodynamic system with temperature and entropy. This insight begins with the laws of black hole mechanics, formulated in the early 1970s. They link changes in horizon area to changes in the Hollier-Eurostrade-S mass, angular momentum, and charge in a way that closely mirrors the familiar laws of thermodynamics. When Hawking radiation is added, this similarity becomes a precise identification. The surface gravity at the horizon is proportional to a temperature, and the horizon area is proportional to an entropy. For a non-rotating, uncharged black hole, the entropy is roughly 1/4 of the horizon area in Planck units. This is far larger than the entropy of ordinary matter of the same mass. The edge, therefore, encodes an enormous amount of microscopic information, though the detailed degrees of freedom remain uncertain. In many approaches, each tiny patch of horizon area acts like a quantum cell. and the full horizon resembles a statistical ensemble of edge configurations. The thermodynamic behavior of horizons suggests a radically different way of thinking about edges, explored through holographic dualities. In certain highly symmetric universes, gravity in a volume of spacetime appears to be equivalent to a non-gravitational quantum theory defined on a lower dimensional boundary. In such dualities, a black hole in the bulk corresponds to a hot thermal state in the boundary theory. The event horizon Eurostrade S area and its changes map to the entropy and dynamics of that field theory state. The edge of the black hole is then reinterpreted as a kind of emergent surface, arising from collective boundary behavior rather than fundamental geometry. Careful work in these models has reproduced aspects of Hawking radiation, quasi-normal mode ringing, and scrambling of information. While our own universe does not match the exact conditions of the best understood dualities, these examples give concrete support to the idea that horizon edges may be manifestations of deeper, non-geometric quantum structures. The edge becomes a bridge between seemingly different descriptions of the same underlying physics. Microscopically, the edge of a black hole behaves like an extremely efficient mixer of information. Perturbations dropped in from outside become rapidly spread, or scrambled, across the horizon Eurostrade S degrees of freedom. In many theoretical models, black holes saturate a conjectured bound on how fast quantum information can scramble, with characteristic timescales scaling roughly with the black hole Eurostrade S radius times a logarithmic factor. This fast scrambling is tied to chaotic features in the dynamics near the horizon. Small differences in infalling states can lead to exponentially diverging internal configurations, even though the external classical geometry remains smooth. Observationally probing this chaos is challenging. Indirect signatures might appear in subtle correlations within Hawking radiation or in the detailed patterns of gravitational wave echoes, though present data are not yet precise enough to test these ideas. The concept of the edge as a maximal scrambler influences models of quantum gravity, quantum computation, and even analog laboratory systems where horizon-like behavior is engineered using fluids, light, or cold atoms. Because true astrophysical black hole edges are distant and extreme, researchers explore horizon physics in controlled analog systems on Earth. These systems do not reproduce full gravity, but they mimic aspects of wave propagation near an effective horizon. One example uses flowing fluids or Bossier-Uros, Einstein condensates, arranged so that the flow speed exceeds the characteristic wave speed in a region. Waves trying to move against the flow are swept inward beyond a point that acts like a one-way boundary. Similar behavior appears in optical fibers, where changes in refractive index create moving horizons for light pulses. In several experiments, researchers have reported emission with properties reminiscent of Hawking radiation, though at far higher effective temperatures and with different microscopic origins. These studies help test whether horizon-related particle production is a robust kinematic effect rather than a specific feature of gravity. They also provide insight into how dispersion, dissipation, and quantum coherence might modify edge phenomena compared with the idealized predictions of general relativity and quantum field theory in curved spacetime. The edge of a black hole raises subtle questions about what it means to observe or measure a physical system. For a distant observer, any object approaching the horizon appears to slow and fade, never quite crossing in finite external time. For an infalling observer, the crossing is uneventful in classical theory. These two descriptions are both valid within their own frames, yet their coexistence seems to create tension in discussions of information loss. Some approaches emphasize that no single observer can access both descriptions fully, so there is no operational contradiction. Others use this tension to motivate new principles, such as black hole complementarity, in which the interior and exterior descriptions are treated as different, mutually inaccessible accounts of the same underlying quantum reality. In this view, The edge is not a simple geometric surface, but a locus where observer-dependent descriptions transition. Thinking carefully about which measurements are possible and by whom helps clarify how much of the apparent paradox is physical and how much reflects the limits of combining classical spacetime intuition with quantum theory. Many proposed alternatives or extensions to general relativity alter the nature of black hole edges. Some theories introduce additional fields that can modify the structure of horizons or generate new types of hair, giving the black hole more observable parameters than mass, spin, and charge. In scalar euros, tensor theories, for example, a scalar field may accumulate near the horizon, changing the effective geometry and potentially shifting the location of the edge, as seen by test particles or light. In some higher curvature theories, the relation between entropy and area is modified, suggesting that the microscopic interpretation of the horizona Eurostrade S degrees of freedom also changes. There are models where the would-be horizon is replaced by a very compact, horizonless object with a surface only a tiny distance outside the classical position. These constructions aim to resolve information puzzles or avoid singularities, but they must also match precise astrophysical observations. Gravitational waveforms, black hole shadows, and accretion signatures provide ways to constrain how dramatically the edge can differ from general relativistic expectations. If small black holes formed in the early universe, their edges would have been environments with far higher effective temperatures than those of stellar mass or supermassive black holes. A black hole with the mass of a mountain would have a radius of roughly a billionth of a meter and an associated Hawking temperature high enough to emit significant high-energy radiation. Still smaller primordial holes, if they existed, would evaporate even faster, potentially disappearing long before galaxies formed. Their edges would have been intensely dynamic, with mass shrinking on timescales comparable to or shorter than the time between emitted quanta. Such evaporation could leave imprints in the form of diffuse gamma-ray backgrounds or contribute to cosmological relics, though current limits restrict how abundant these primordial black holes can be. The detailed microscopic behavior of the edge during the final stages of evaporation remains uncertain because quantum gravity effects become significant. Here, the classical picture of a smooth horizon is almost certainly inadequate, and speculative models range from gentle fades to explosive finales. Modern numerical relativity provides a practical way to explore black hole edges by evolving Einstein-Eurostrade S equations on supercomputers. In these simulations, the event horizon is not always directly tracked, because doing so requires global knowledge of the spacetime. Instead, researchers often use apparent horizons, which can be located using data on each time slice. The apparent horizon approximates the true edge in many dynamical situations, especially once the system settles. Simulations of black hole mergers reveal how these horizons form, grow, and distort as two individual edges coalesce into one. Fine structures appear, small bulges, transient necks, and quasi-normal ringing patterns. By following fields and matter near these evolving edges, researchers connect the detailed geometry to observable signals such as gravitational waveforms and possible electromagnetic counterparts. These computational studies test analytic predictions about horizon areas, surface gravities, and stability, and they highlight regions where strong field, nonlinear behavior may reveal departures from simpler approximations used in many theoretical models of black hole edges. On extremely long timescales, the destiny of a black Hollier-Eurostrade S edge depends on its environment and on the ultimate laws of physics. In the standard semi-classical picture, an isolated black hole slowly loses mass by emitting Hawking radiation. Its event horizon shrinks, its temperature rises, and its evaporation speeds up as it becomes smaller. For a stellar mass black hole, this process takes far longer than the current age of the universe, roughly 10 to the 64 years or more. For supermassive black holes in galactic centers, the timescale is even longer, extending far beyond 10 to the 100 years. In a universe that keeps expanding and cooling, black hole edges could become among the last active structures, gradually vanishing into faint radiation. Quantum gravity may change this story, perhaps leaving stable remnants or altering the late stages of evaporation. Our present understanding can follow the edge evolution only up to a point. Beyond that, the final chapters of what happens at the edge remain open, guiding ongoing exploration in theory and observation. In the quiet centers of dense star clusters, the edge of a black hole is not an isolated feature, but part of a crowded gravitational ecosystem. Stars, stellar remnants, and dark objects move through orbits that occasionally bring them close to the event horizon of an intermediate or massive black hole. Over millions to billions of years, gravitational interactions slowly scatter these objects, and a small fraction is deflected onto plunging trajectories. Each near miss and eventual capture traces a path through curved spacetime, briefly sampling the region just outside the horizon. The edge acquires a subtle structure in phase space, a distribution of possible orbits, energies, and encounter geometries. Encounters between compact objects and the whole can generate bursts of gravitational waves, and if gas is present, flashes of electromagnetic radiation that probe conditions a few gravitational radii from the horizon. In such environments, the edge is shaped not only by the black Hollier-Eurostrade S own mass and spin, but also by the long-term statistical behavior of thousands to millions of neighboring bodies orbiting around it. When a star passes sufficiently close to a massive black hole, tidal forces can exceed the star-Eurostrade S self-gravity and pull it apart in a tidal disruption event. Whether this tearing happens outside the event horizon or hidden inside depends on the star-Eurostrade S density, the black Hollier-Eurostrade S mass, and its spin. For black holes lighter than roughly 100 million solar masses, a solar-type star is usually disrupted just outside the horizon. Half of the stellar debris becomes unbound and escapes, while the remaining fraction falls back, circularizes, and forms a temporary accretion flow that can glow across the electromagnetic spectrum. The newly formed disk extends down to a few gravitational radii, with its inner edge set by the black Hollier-Eurostrade S spin, and its outer regions tracing the spread debris. The rise and decay of the flare over weeks to years carry information about the geometry just outside the horizon. In this way, each disrupted star serves as a brief, violent probe of the edge, revealing how gravity, hydrodynamics, and radiation interact there. Between stellar mass and supermassive black holes, there is a suspected population of intermediate mass black holes with masses from roughly 100 to 100,000 suns. Evidence for them remains uncertain and often indirect, inferred from unusually bright X-ray sources, star cluster dynamics, or gravitational wave mergers. If such black holes are common, their edges occupy an intermediate scale where both strong field gravity and more ordinary astrophysical environments meet. The event horizon of a 1,000 solar mass black hole is only a few thousand kilometers across, yet it could sit in a relatively low-density region of a star cluster or dwarf galaxy. Accretion flows here may be patchy, intermittent, and influenced by individual stars rather than by smooth galactic gas. The edge would thus flicker between phases of near quiescence and brief bursts of activity. Because variability timescales scale with mass, changes near these horizons play out over seconds to hours, faster than in galactic nuclei, offering more rapid natural experiments in strong gravity and plasma behavior at the boundary. At the cores of active galaxies, supermassive black holes are surrounded by luminous accretion disks, hot coronas, and broadline gas clouds. In these environments, the edge of the black hole is continuously fed by inflowing matter, and the region just outside the horizon becomes a complex, multi-component structure. X-ray emitting coronas sit within a few tens of gravitational radii, bathing the inner disk in high-energy photons that scatter off electrons and reflect from dense gas. Ion emission lines from the disk are broadened and skewed by orbital motion and gravitational redshift, encoding how close the luminous material extends toward the horizon. Reverberation mapping, which tracks time delays between variations in the corona and disk response, can constrain the size and structure of this inner region. The edge here is not a sharp boundary in brightness, but a gradual transition where thermal disk emission, coronal scattering, and sometimes jet formation overlap. These layers together form a dynamic, stratified atmosphere around the horizon, responding to changes in the accretion rate and magnetic field configuration. When two black holes orbit each other, each has its own event horizon, but their gravitational fields intertwine. Far from the pair, spacetime can be approximated by a single distorted geometry, yet near each black hole, the local edge still behaves much like that of an isolated object. During the inspiral, tidal deformations of each horizon remain modest for comparable mass binaries, according to numerical relativity simulations. As the black holes approach merger, their horizons stretch and begin to form a common apparent horizon that encloses both. The detailed geometry of this newly formed surface, evolving on timescales of a few light-crossing times, is encoded in the gravitational wave signal. Ringdown modes after merger reflect how the final horizon settles into a nearly stationary shape, determined mainly by total mass and spin. Close to the merger, spacetime curvature peaks in a region that briefly encompasses what used to be the individual edges. Although these dynamics are difficult to probe electromagnetically, gravitational waves allow indirect inferences about how horizons interact and reconfigure. An extreme mass ratio inspiral involves a stellar mass compact object, such as a neutron star or small black hole, orbiting a supermassive black hole while slowly losing energy through gravitational radiation. Its orbit can dip very close to the larger Hollier-Eurostrade S event horizon, tracing complicated, processing paths over tens of thousands to millions of cycles before final plunge. From the smaller objector Eurostrade S perspective, the horizon is a vast, slowly curving surface, while from far away the system appears as a faint, persistent gravitational wave source. Planned space-based detectors like LISA aim to record these low-frequency waves with enough precision to reconstruct the spacetime geometry around the massive black hole. The detailed pattern of frequency evolution and modulation will reveal how closely the environment matches the predictions of general relativity. In particular, the late stages before plunge are sensitive to the location of the innermost stable orbit and the spin-induced shape of the edge. Thus, these inspirals function as precise cartographers of the Horizona-Eurostrade S surrounding geometry. In some systems, matter falls toward a black hole at rates exceeding the classical Eddington limit, where radiation pressure would balance gravity under simple assumptions. Such super-Eddington accretion likely occurs in certain ultraluminous X-ray sources and during brief phases of tidal disruptions or rapid black hole growth. In these regimes, radiation becomes trapped within thick, turbulent flows that can form extended funnels along the spin axis. The region near the horizon is then obscured along some lines of sight by optically thick gas, while along others it may remain partially visible. Numerical simulations suggest that strong outflows are launched from radii of a few to tens of gravitational radii, carrying away mass and angular momentum. The effective edge, as seen by radiation, can therefore lie outside the true event horizon, defined instead by where photons can begin to escape the dense, scattering medium. This radiative photosphere varies with time and direction, creating a horizon environment that is both anisotropic and intrinsically time-dependent, shaped by the interplay of gravity, radiation, and magnetized turbulence. Even in regions far from bright galaxies, black holes exist within a bath of low-level radiation, including the cosmic microwave background and diffuse extragalactic light. For an isolated black hole, this ambient field slowly drifts inward, with some photons captured and others deflected. Over cosmological timescales, such accretion is extremely weak, adding negligible mass for stellar or supermassive black holes. However, the presence of background radiation establishes a reference environment for phenomena like Hawking radiation. For astrophysical black holes much more massive than roughly a lunar mass, the Hawking temperature is far below the temperature of the cosmic microwave background today, so absorption dominates over evaporation. The edge thus acts more as a sink than a source thermodynamically. As the universe expands and the background cools, there will come an epoch far in the future when the cosmic temperature drops below the Hawking temperature of some black holes. At that point, their edges will transition from net absorbers to net emitters, slowly reshaping their surroundings through ultra-weak quantum radiation. In galaxies and clusters, black holes sit within extended halos of dark matter whose microscopic nature remains unknown. Although dark matter interacts mainly through gravity, its distribution and motion influence the environment of the event horizon. Over time, dark matter particles can scatter gravitationally and form density spikes near central black holes, depending on their initial profile and the history of mergers. Dark matter is made of weakly interacting massive particles that can annihilate with one another. Enhanced densities close to the black hole could lead to increased annihilation rates. The resulting gamma rays or other products would originate from regions that may extend down to a few gravitational radii. Alternatively, if dark matter is ultralight and behaves like a coherent field, it can form large-scale condensates and possibly undergo super-radiant instabilities around spinning black holes. In that case, the edge interacts with a macroscopic field configuration, exchanging angular momentum. Observations placing limits on such effects indirectly constrain the properties of the dark matter surrounding the horizon. When galaxies merge, their central black holes are brought together within a common envelope of gas and stars. During the inspiral, tidal torques can drive gas toward the center, enhancing accretion and lighting up active galactic nuclei. The edges of the two black holes may be temporarily embedded within a shared circumnuclear disk, where shocks, turbulence, and magnetic fields reshape the inflowing material. The combined activity can launch powerful outflows and jets that propagate through the host galaxy, heating and expelling gas. This feedback process affects star formation and the buildup of galactic structure. The horizon itself remains small compared to galactic scales, but its influence is amplified by the energy released per unit mass accreted. Over time, a correlation emerges between black hole mass and galactic bulge properties, suggesting a long-term coupling between edge-scale physics and galactic evolution. Simulations that include both detailed accretion physics near the horizon and large-scale dynamics aim to track how local processes at the edge translate into global feedback across tens of thousands of light years. On the largest observable scales, matter in the universe arranges into a cosmic web of filaments and nodes. At the intersections of these filaments, clusters of galaxies host many supermassive black holes embedded in hot, diffuse gas. As material flows along the filaments toward these deep potential wells, some fraction eventually reaches the vicinity of black hole horizons. The edges thus act as terminal points for matter that has traversed millions of light years. X-ray and radio observations of galaxy clusters show cavities, shock fronts, and extended radio lobes inflated by jets originating near central black holes. Energy deposited by these outflows helps balance radiative cooling in the intracluster medium, regulating how gas condenses and forms stars in central galaxies. In this way, microscopic processes at and near the event horizon, such as magnetic reconnection in the inner disk or jet launching, shape the thermal and dynamical state of gas on scales of hundreds of kiloparsecs. Each edge, though small, participates in maintaining the energetic balance of entire regions of the cosmic web over billions of years. As attention turns from present telescopes to distant futures, the edge of a black hole begins to appear not only as an object of study, but as an environmental condition that any longer Euros-lived technological civilization might eventually confront. On timescales far beyond the age of current galaxies, stars will fade, gas will be exhausted, and black holes will come to dominate the energy landscape of the universe. Some researchers have speculated, cautiously and with many caveats, about how advanced beings might use regions just outside event horizons. The steep gradients of gravitational potential and the concentration of magnetic and radiation energy near the edge suggest natural reservoirs of free energy. Concepts such as Dysona Euros, like constructions that harvest the glow of accretion flows, or engines that slowly lower and raise matter in a gravitational field to extract work, rely on Euros' understood general relativistic principles, though their practical realization remains extremely speculative. In that far future, the edge would no longer be only a boundary in spacetime. It would also be one of the last active interfaces where complex structures could interact with a cooling, thinning cosmos.